Okay, good afternoon. Welcome everyone here at NIWA in Auckland and around the world on our webinar. Welcome to the latest in a series of webinars from the Woodsmoke Researchers Network. We've had a number of talks on a variety of topics, all of which can be found on the Woodsmoke Network website. And at the end of today, you'll find an additional talk on their website. But today we're going to hear from Jane Clougherty. Jane is an associate professor at Drexel University in Philadelphia, but also has been a regular visitor to New Zealand. I think this is her 11th visit.
Indeed.
And today she's going to talk a little bit about a pilot scale study we've been doing together here in Christchurch in New Zealand and how it relates to some of the previous work and ongoing work around the world. So over to Jane.
Fantastic. Thank you, Ian, and thank you everyone for being here today, both in the room and on the web. I appreciate all of your time and thought and attention for joining us. And of course, I'm especially going to thank the folks here at NIWA, who, as always, are a joy to work with and did so much great work to pull this webinar series together. So the work that I'm going to be sharing today is really pilot scale research that we've done in the Christchurch area to try to understand spatial variation in exposures to wood smoke, which is a really critical exposure in and around the Christchurch, Canterbury region. And one of the unique things that we've tried to do is to really separate the spatial pattern in what air pollution looks like during the daytime versus nighttime in that region. And then we'll think about how that applies to health effects studies and thinking about susceptibility as well. So I think this is my pointer. My mistake. Okay, we can do this. Alrighty, so as all of you, I'm sure, are very much aware, ambient air quality has been associated with an enormous variety of health effects to date. Predominantly, respiratory and cardiovascular disease have been researched for a very long time, but increasingly we're seeing results coming out on things as varied as birth outcomes, cognitive outcomes, life expectancy as well. And one of the really fascinating things, we certainly find this in the US, is that the effects of air pollution, and fine particles in particular, tends to vary from place to place. So the association between fine particles in one city may not be the same association you would see elsewhere. And we don't actually know, is this a combination of the fact that sources are different from place to place, and therefore the chemical composition of particles is different from place to place? Or is it the fact that populations are different and their susceptibility patterns are different? So therefore, we might want to try to tear these things apart. So today, as I promised, we'll be talking about the design and the results of a pilot campaign we've done in Christchurch. We'll be talking about tracers for wood smoke exposure, day and night patterns, but then we'll go into this area of epidemiology, thinking about how we would extend such a study in the future, how it would help us improve the epidemiology that we do, and how it would help us tear apart susceptibility versus exposure effects on health here in New Zealand. Okay, so for most of the folks in the room, you're familiar with the location of Christchurch, but for the folks who are listening around the world, Christchurch is a medium-sized city, about 320,000, I think, currently, on the east coast, midway down on the South Island of New Zealand, within the Canterbury region. As many of you are aware, there was a series of earthquakes, most notably in February of 2011, that did do an enormous degree of damage to the infrastructure of the city, but they've been doing an extraordinary job of recovering since then. One of the persistent problems in Christchurch, of course, has been air pollution exposures, but that's really not a new problem. That's been in place for quite a few years. As you can see here, this is annual average PM10 data from just one monitor in the Christchurch area. This is a regulatory monitor run at St. Albans or Coles Place, which is a residential community north of the CBD, Central Business District. And what you'll see here is from year to year, 2007 to approximately the present, the annual average concentrations do go up and down a little bit, but not drastically. You'll see there was a bit of a spike in 2011 when even more so than now, people truly were relying on wood burning for heat in the wintertime. You'll notice that as we think about these trends over the course of the year, the monthly average PM does differ quite a bit. And you'll see here that the highest levels are from June through August, which of course in the Southern Hemisphere is winter. It's always a shift we have to make. And because I come back and forth to New Zealand fairly frequently, I usually don't know what month it is. So shifting from the Northern and Southern Hemisphere, we need to remind ourselves. So we see the bulk of PM concentrations happening during the winter months in Christchurch, and you'll see that there's an inverse association with monthly average temperature on the top. So that makes sense. When it's cold out, people are burning more wood for heat. One of the further interesting things about the PM, or the air pollution pattern in Christchurch, is that there's a huge diurnal or within-day variability in the concentrations that we'll see. So this is again data from a residential community north of the CBD. And what you'll see here in nitrogen oxide, nitrogen dioxide, is that there are distinct peaks in the morning, right around 9:30. So that looks like the rush hour that we see in many cities around the world. But then there's this other huge peak happening about around 7 o'clock p.m. So it's after the rush hour. What else could be happening? Well, everyone's getting home and booting up the wood burners. And that's when we see these enormous increases in emissions that then do somewhat dissipate over the course of the evening. And that's one of the things that we wanted to explore better in this pilot. So really, those hours were of particular interest to us. In the pilot, as we go forward, this really is the background as to how we picked the two different sampling intervals that I'll show you. One is a daytime sampling interval, 7 a.m. to 5:30 p.m. One is overnight, 7 p.m. to 5:30 in the morning. And thank God I was not in the field at 5:30 in the morning. But to talk about the study design a little bit, I've alluded several times already to why we did the study and why we thought about designing it in the way that we did. So clearly we had two goals. One is to understand the daytime and nighttime spatial patterns and compare those. And the other is that we wanted to get much more refined in how we measure wood smoke. So in many locations in New Zealand, by relying on regulatory data, which is incredibly important and incredibly high quality data that all of the regional councils put a tremendous amount of effort into collecting, oftentimes, due to the regulatory standards in New Zealand, it's really just PM10 concentrations. There's not yet a PM2.5 standard, so that data is not available in many locations. And there is less data available than we wished there was on elemental inorganic tracers. So these are the components that make up fine particles and give us a better clue as to where those particles are coming from. So we wanted to get into those source tracers a little bit more clearly. For wood smoke, there's very good evidence linking levoglucosin in the literature to both spatial and temporal patterns in wood smoke exposures. It's a very good tracer for wood smoke. Arsenic is a good tracer really for treated wood because of CCA treating. Potassium is frequently used as well. For diesel, which is one of the important exposures we wanted to be able to separate wood smoke from and to understand the layering of impacts of wood smoke on top of the urban mix, bearing in mind that Christchurch has literally been rebuilding itself over the past 6 years. There's an extraordinary amount of construction activity, which means a lot of diesel, a lot of crustals resuspension in the city. So for those, we pulled some tracers in the organics fraction of PM. We allocated 9 sampling locations across space. We ran one site over the whole month that we sampled so we could adjust everything else. We ran an additional 15 sites for nitrogen oxides, really because we can do these passively. They're a general combustion indicator, and they give us a little bit richer spatial pattern across the city when we need it. We sampled for 3 weeks. These are all 7-day samples, so they're integrated samples, which means it's one filter that gets exposed every day for 7 days. And this was in May 2014. We ran a nighttime sample, a daytime sample at every location. At 6 of these sites, we also did something that was a little bit more unique, perhaps. We ran a quartz filter, which really allows us to sample for organics, focusing on levoglucosin, our best wood smoke tracer. And we separated monitoring the evening hours when we hypothesize that much of the wood burning is active burning from the overnight hours when we expect that a lot of those fires are dying off and really kind of looking at the smoldering periods. We wanted to see whether or not the concentrations that we would see in the city were different during those hours. So this is what our site selection finally looked like. The traffic, let's see, low wood burning, low traffic is the lightest category. Add some traffic to that, so you have low wood burning, high traffic. That's the next lightest shade category. Then we had high wood burning, low traffic, high wood burning, high traffic, and of course high on both exposures are the darkest categories that you see across the map. The reason we wanted to understand this spatial patterning in GIS, Geographic Information Systems, before we did our site selection is because we really are one of the few studies in the world that has tried to understand effects of wood smoke in an urban environment. So we're literally trying to understand the effects of wood smoke on top of the typical urban mix that we see everywhere, which is frequently very much driven by traffic and diesel. So we needed to be able to separate those a little bit. And this is what our final site allocation looked like. For fine particle sampling, we had 9 sites allocated across the Christchurch area, 2 that are effectively in the CBD, Central Business District, and then really kind of in a ring around that area, reaching into the residential communities, but all of those categories, color-coded categories I just showed you, are represented by those sites. I mentioned that for our passive samples for nitrogen oxides, we were able to do a larger number of sites, so we did. And those, like the fine particle samples, are switched, so we have daytime, nighttime patterns at all of those locations. Wind speed and direction. Meteorology is the one thing that we cannot design before we go into the field. We can do our best to look at historical meteorology and design our studies keeping that in mind, but we are at the whims of chance once our samples are already in the field. When we're sampling over across only 3 weeks and a relatively small number of sites, we are in a very tricky space to do what we would call a temporal adjustment on our data to look more clearly at the spatial pattern. So dealing with the meteorology and the temporality is quite tricky in this case. In a sense, we lucked out that we had each of the possible wind paradigms represented. You'll see that during week 1, the winds were predominantly from the southwest. During week 2, the winds were predominantly from the northeast, some switching in both cases, but it's really quite convenient that we have both wind paradigms represented and evened out in our data. Sample 3, we kind of got winds from both directions. And by sample here, I mean that interchangeably with week. So that's week 1, week 2, week 3. Daytime on the top, nighttime on the bottom. And here's what we saw. When we take all of the data, temporally adjusted, and look at it in sum, we see that for fine particles, that's PM 2.5, the particles that go all the way down to the alveoli, to the base of the lung, most directly associated with health effects, you'll see that we have nighttime concentrations in every week that are substantially higher than the daytime concentrations in that week. Likewise for levoglucosin, and that difference is a little bit stronger even. The nighttime concentrations are quite a bit higher than the daytime concentrations on every week. And then finally, we looked at arsenic, again, an indicator of treated wood burning. And no surprise, once again, we see higher concentrations each of those 3 weeks compared to the daytime concentrations. Okay, so paired day and night samples for these 3 pollutants, at least, not for all of them, we consistently see the nighttime is quite a bit higher. When we look at the averages and standard deviations across all of our pollutants that we measured during daytime sampling and nighttime sampling, and then look at the statistical difference between the two, for the vast majority of our pollutants, even on a small sample size, they were statistically significantly different. And they really were quite shockingly different, which is what's really important here. The ratios between nighttime and daytime are really quite high in some cases. So I'll bring your attention all the way down to the bottom, of course, to levoglucosin to start, and you'll see that our nighttime concentrations are 6 times our average daytime concentrations. So the measures really are quite different. For the vast majority of our pollutants, they are higher overnight, but there are a number that are higher during the daytime. NO2, our total combustion indicator, as well as calcium, iron, manganese. Those are effectively, calcium especially, crustal elements. So these are indicators of resuspension, construction activity, general combustion in NO2 from traffic or diesel. These are the kinds of activities that are higher during the day, significantly so. And then most of everything else really is higher quite a bit overnight. Focusing in on levoglucosin just a little bit, this is what we saw in the daytime versus the nighttime pattern after adjusting for that fact that we were sampling across 3 different weeks. And you'll see that during the daytime, we generally see lower concentrations of levoglucosin in the city core, and then higher concentrations in the outskirts. Likewise, at night, really a very consistent pattern. Lower concentrations in by the CBD, higher concentrations in the outskirts, particularly in the residential communities. But what's really important here is please take note of the legend. So you'll see the range here in, I think this should be nanograms per meter cubed. I apologize on the units. The range is going from 0.1 up to about 0.6, and overnight going from about 0.7 up to about 2.8. So what we're seeing there is that actually the range is such that the lowest concentration at night is higher than the highest concentration during the day, although the pattern is remaining consistent. Alrighty, nitrogen dioxide, again, many more sites, daytime, nighttime. And I'm going to point out that effectively we're seeing the opposite thing. The spatial pattern holds quite consistently day to night, but all the concentrations are much higher during the daytime than during the nighttime. And then finally, calcium. Again, I mentioned this is a pretty good tracer for crustal resuspension, and you'll see, as previously, somewhat of a comparable spatial pattern. It's not quite as distinct because the contrast isn't quite as distinct in concentrations across the city, but generally higher concentrations daytime than nighttime. I mentioned that we were interested in what was happening during the active burning phase versus the smoldering phase of wood burning. So here what I'm showing you are the concentrations during those hours between 7 p.m. and 12 a.m. Let's concentrate on the center column for a moment. So that's the evening. And then these are the overnight hours from midnight until 5:30 in the morning. And we'll see that for the vast majority of our pollutants, again, things are really quite a bit higher in the evening than overnight. That's not shocking for many of these pollutants that were originally pulled out to look at traffic and with a particular interest in diesel. We would sort of expect more activity in those pollutants during the evening than during those very, very quiet overnight hours. And there really is no nightlife in Christchurch. There's nothing happening overnight. But there are a few pollutants that we see higher during those smoldering periods, including the hopanes and colistanes, generally diesel indicators. That could be activity picking up in the very, very early hours. The levoglucosan, of course, is our primary interest here. It is indeed higher during active burn than during smoldering, but the values aren't quite as distinctly different as we expected. We're looking at effectively 17.0 versus 14.4, and there is overlap in those confidence intervals. So we're not seeing as shocking differences between those periods as we might have expected, but perhaps that's in keeping with the literature. And that's something that we're thinking about more and thinking about when we might expect the predominance of levoglucosan to be released in the PM that we're capturing. Alrighty, so I'll add a few thoughts on spatial modeling for air pollution and how we might think about going forward, building a larger study, collecting a wider suite of sites, and what we could do with that data. So some of you may be aware with a technique called land use regression. So what this effectively means is that once you have a large number of sampling sites across your city, you can build a huge suite of GIS, geographic information systems, based covariates that describe those locations. Traffic density within 500 meters, truck traffic density within 1,000 meters, wood burner density within, pick your distance, population density, et cetera, et cetera, et cetera. This is a list from a study that I did in the Pittsburgh area. We would, of course, in this case, add covariates to it. That would be things like wood burner density, chimney density, other indicators that would help us understand the patterning in burning activity across the city. Once we have those covariates built at all of our sampling locations, we can look at how they relate to the concentrations that we measured at each of those locations and build a model where we're describing the pollution concentrations we see as a function of all of these spatially distributed sources. And once we have that model in place, we can use it to predict or estimate concentrations everywhere else in the city and build beautiful, smooth spatial surfaces that allow us to estimate pollution exposures to people at a very fine spatial scale. This is one example from the literature that's been done for levoglukocin. This was in the Seattle, a large urban area in Washington State in the northwestern part of the US. And this was built off of a combination of mobile monitoring and fixed site, that is a monitor that stays in one location, data. And you'll see that they were able to estimate concentrations in levoglukocin during what would be likely high burn hours, 9 p.m. to 3 a.m., across their entire urban area. So you can see what the pattern looks like in their overall highway patterns. Their monitoring sites are marked in circles here, and you'll see that there is quite a bit of variation that they were able to observe across the city, and they were able to build a smooth surface across all of their sampling sites because they were working across a larger number of sampling sites than we currently are. There are other studies, such as this one in Montreal, where they have been able to identify, using that land use regression approach, those predictors which most strongly explained pollution across their urban area. In this case, chimney density was the strongest variable that came up for them. So this is just a map of their chimney density variable. You'll see that in this case, they're working at somewhat of a large scale. They have bigger grids here, and we would usually like to see much finer, smaller grids and more resolution within the urban area. In many cases, including in Christchurch, where we're lucky enough to have a beautiful wood burner census that has been done, we could conceivably get much finer scale and much smoother, more refined, more precise in those surfaces. And then the last example I'll show you, based on wood burning, was done by some colleagues in Vancouver, where they looked at light scattering. So this is really an indicator of PM, but they did show some very strong associations between PM and wood burner density and levoglukocin in their region. And you'll see that they were likewise, off of a large number of sites, they did this by mobile monitoring, able to build a nice smooth spatial map to estimate exposures at any location within the city. One of the really neat things that they did thereafter was to think about, well, how does the spatial pattern in potential exposures correlate with the spatial pattern in potential susceptibility of the population? So they used an income indicator as a proxy for socioeconomic status to try to understand something about susceptibility. And sure enough, what they found, as they hypothesized, was that they had lower average intake fraction. That's an estimate of how much of the pollution is being taken in by the population in that area, decreasing intake fraction as income increases. So they pointed this out as a potential environmental justice issue related to wood burners and certainly reliance upon wood burning for heat, certainly related to many of the fuel poverty and related issues that we hear about in many countries around the world struggling with today. So I'll talk just a little bit more about spatial patterning in exposure and susceptibility and a few of the potential applications that we could think about as we grow this study in Christchurch and think about enriching the data set. This data is from a study I participated in several years ago, conducted by New York City Department of Health and Mental Hygiene. And there we monitored a large number of sampling sites all around the city, 150 sampling sites for a large number of pollutants, and we're able to build beautiful smooth surfaces from that data, which has supported some excellent epidemiology we've been able to do since, and of course are continuing to do. On the top, what you'll see is a spatial deprivation index that we built using census data in the US. And this includes indicators of income, education, and other variables related to socioeconomic status. We built that using Lynn Messer's approach that she developed at UNC. Putting those together is the surprise in New York. And I raise this just as something to be aware of as we're thinking about spatial patterns in exposure and susceptibility. What we found in New York is those really aren't always the same. They are in many cities, but not always. In New York, you'll see that the least deprived census tracts had the highest and most variable nitrogen dioxide exposure. And then it increased somewhat as those census tracts got a little bit less wealthy, and then gradually very, very, very gradually, you can barely see it, increasing as you go across the trend. And what this said to us is that New York is the unusual case where the highest exposures were actually happening in some of the wealthiest communities. In and around the downtown area in Manhattan, the highest concentration census tracts that we found were actually the Upper East Side of New York. It is literally comprised of the wealthiest census tracts in our country, and they also happen to have very, very high air pollution exposures. And those air pollution policies changed in about a year after we released this map. But my point is, once you have these beautiful fine-scale spatial surfaces, which we hope eventually to move towards in Christchurch and other parts of New Zealand, including Auckland, we're able to do much more refined epidemiology. So you'll see here smooth trends looking at the association between nitrogen dioxide and birth weight. We published this paper a few years ago to make a very important point, that that association between nitrogen dioxide and birth weight looks like a very different trend depending upon whether you're looking in neighborhoods of high socioeconomic position, medium, or low socioeconomic position. And these were really challenging plots to understand. We were really lucky in New York that we have a massive population, so we have these huge sample sizes that underlie these data sets. So we're able to look at everything non-linearly and in complex functions. We ran all of this nonlinear, so we allowed for these unusual trends to appear in the data. And you'll see that in both the wealthiest and the poorest communities, nitrogen dioxide is associated with lower birth weight. That's curious. In the middle class communities, we saw no association whatsoever between NO2 and birth weight. In the poorest communities, perhaps there's where we can hypothesize a susceptibility effect, that there really is quite a distinct gradient between nitrogen dioxide and birth weight in those communities that may be most susceptible. This was challenging for us. How do you think about strong relationships, nonlinear, complex relationships between nitrogen dioxide and birth weight in a wealthy community? In some cases, a very wealthy community. Well, we think that a big part of the answer is probably here. So it was really important for us before moving forward in that study to understand how air pollution and poverty pattern together and how they may be confounding each other or play out in the epidemiology before we could move forward and interpret these very different patterns that you see depending upon the susceptibility of the population you're looking at. In Christchurch, and I apologize, this map is a little bit fuzzy, we do of course have variation in income, as we do in every city around the world. You'll see here, this is mesh block level median income, and it ranges from, well, 0 to 10,000 in the very lightest areas, so very poor communities, up to incomes of 40 to 55,000 New Zealand dollars. And what you'll see here is there really is a distinct patterning in income across Christchurch, with some of the wealthier communities up in the Northeast. And this is not entirely independent from the patterns that we've seen in wood smoke exposures. And again, recall that we're looking at things like arsenic that may be tracers for burning treated woods or woods that aren't supposed to be used in your wood burner. So there are some really interesting environmental justice issues potentially underlying this patterning that we want to understand, first of all, in who is burning, i.e. relying on wood burning as their primary heat source. What are they burning? Is it treated wood or is it clean wood? That certainly is a product of fuel poverty concerns. And then finally, how susceptible are they to the health effects that are produced? So it's a very, very complex situation in Christchurch. And of course, it's been an evolving one over these recent years. Some of you may have seen this study that was just released about a month ago here in New Zealand. And what the authors wanted to understand was the association between wood smoke, and they used the census wood burner density variable that I mentioned as their predictor, and the likelihood of a child having an emergency department visit for something that could be related. What they used here was non-accident related emergency department visits. So this is the child breaking his legs on the playground. These are outcomes that could potentially be related to wood smoke. Again, wide variety of outcomes associated with air pollution. And they're looking at the variation in the odds ratio here between the exposure, again, estimated by wood burner density in the child's mesh block, and their odds or their likelihood of having an emergency department visit sometime between birth and age 3 years. And you'll see up at the top is really the most important trend. Those first 3 dots, what that's showing you is as you go from the reference quartile of having the lowest wood smoke or coal smoke estimated in the mesh block up to the highest, the 4th quartile, you see a consistently increasing trend in the likelihood of that child having a non-accident related emergency department visit sometime between birth and age 3. And you'll see that then they really thoughtfully tried to look at other aspects of the child's life. Things like mold and mildew in the child's bedroom, a consistent problem in housing quality in New Zealand. Household hardship, so they did have poverty indicators in here, whether or not the child was in an urban or a rural area, and other characteristics that they hypothesized may alter the relationships between wood burner density and likelihood of an emergency department visit. The strongest association they found was in something that they call an independent urban area relative to a core urban area. I'm not entirely sure, clear yet from my reading of the paper and needing to think about it a little bit further of what an independent urban area may include. These may be some of the smaller cities that you would think about that are sort of satellite cities to the larger urban areas of New Zealand. But for some reason, those children seem to have the strongest relationships between wood burner density and emergency department visits. So this is the last epidemiology result I'm going to show you. And it's drawn from some of the research that we're currently doing in New York. And the reason I show it is it's a very different type of analysis, but here we're able to take advantage of the fact that we have very, very fine-scale spatial estimates of air pollution and to put that together with the excellent day-to-day regulatory data that our Environmental Protection Agency collects and hopefully continues to. And what you'll see here are ozone exposures and their association with asthma-specific emergency department visits citywide. I'll talk about the overall trend to get us started. Lag 0 is the day of the emergency department visit, and we're estimating here the percent excess risk of having such an asthma event per 10 part per billion increase in ozone. And you'll see that in general, we see higher risks as we go out across the lag days. That's 1 day prior, 2 days prior, 3 days prior, and so on. So for ozone, and this is actually in keeping with the literature, we see the strongest effects of ozone on asthma at about 2 to 3 days out, which does make some sense. It's a very strong respiratory irritant. And one of the challenging things we do need to think about in New York as in elsewhere is that ozone, we get higher concentrations in the summertime in conjunction with heat. So we're thoroughly adjusting for heat here, but part of this is understanding multi-day accumulated effects of both ozone and temperature exposures. The reason why this analysis is powerful is for a couple of reasons. One is, again, we're working with very fine-scale spatiotemporal data, so we can estimate the exposures very cleanly in both space and time. And we're lucky to have the statistical power to be able to look at variation within each one of these associations between the day and the likelihood of an asthma visit. And you'll see here, as hypothesized, that the lowest quartile of our socioeconomic deprivation index, they have the least risk. And then as you increase in that socioeconomic deprivation, so you're going from wealthy communities to poorer communities, you see those risks increase quite dramatically. So because we're really looking at day-to-day and location to location variation in air pollution, as well as the outcome, we can get much more specific in these associations here than in a case where we have to rely upon, say, a mesh block level exposure or susceptibility factor, or where we have to aggregate over very long periods of time. So that's one of the many reasons why we're hoping to sort of enrich, refine, and get more spatially precise in these models over time. Okay, so with that, I'm going to wrap up. I'm particularly going to thank all of my colleagues here at NIWA who've been absolutely fantastic to work with on this study. All of the folks back at University of Pittsburgh in my lab who were both helping us with the study or behind the scenes, keeping everything running. I was indeed at University of Pittsburgh until I moved over to Drexel University this past year, which has been an absolute joy. So thank you all for your attention. Thank you for being here today. For the folks who have dialed in from around the world, thank you for doing that. And of course, I'm very happy to take any questions you may have.
Great. Thank you very much, Jane. I'm just going to give the folks watching live online a moment to send any questions through our online forum if you wish. And while we're doing that, I'd just like to ask if there's any questions from the room here in Auckland for Jane. Do we have any online questions at the moment? We have one in the room.
Hi, I'm Mike Jarrett from UCLA. So I wanted to ask, in the Sioux study, they found that there was this effect with elevation. So they used these hydrological models to look at how the smoke is pooling in valleys and whatnot. Have you seen any evidence of that in Christchurch? I don't know anything about the topography there, but is that a concern for your modeling?
Okay, that's a great question, Mike. Thank you for asking. So Mike Jarrett flew halfway around the world from UCLA to be here today in Auckland with us, and we really appreciate that. It's actually a stopover on the way to the ISEE conference regardless. But it's a great question. It's a great point. It's one of the real challenges that a lot of folks have been thinking about with many of these spatial air pollution studies. We are actually thinking in much more detail right now about the role of elevation in an air pollution pilot study we're doing here in Auckland, where we do have complex terrain as well as street canyons, large buildings to think about. Christchurch is really quite flat in the urban area, which is one of the simplifying factors in this study. However, some of the really most affected communities impacted by wood smoke here in New Zealand are in the mountain towns in Otago, up above Queenstown, Arrowtown, and some of those smaller communities that really have incredibly high wood burning densities and concentrations overnight, in part because they have the pooling and pocketing within those valleys, and they're impacted by inversions as well. So I think that's actually one of the great challenges in these studies, and it really is something we need to think about in interaction with some of the source exposures, as well as with the meteorology, obviously, and start to think a little bit more rigorously about how we integrate dispersion modeling over complex terrain as best possible into the design of these studies. For Christchurch, we've lucked out. It's flat. That's a great place to start, but you're right that that's where we eventually need to go.
Thank you, Jane. Any further questions?
I was going to ask one. I was going to say Christchurch is flat, but I've lived in Christchurch, but it does have hills. And it's quite noticeable if you drive up the hill, you drive through the pollution. And it's actually it is quite noticeable. I mean, so they do have hills, and they do have that inversion line that intersects with that population. It's not a great population. It's also more affluent population as well. Yeah. That live on those hills. So yeah. It does affect you. I think it's probably similar. Yeah. But it's a different type of.
Yeah, that's a really important point that you raised, that the change in elevation is also associated with the change in population density or population characteristics. That's certainly something we see here in Auckland, that on the higher, steeper slopes, that's not where the largest buildings are put. So sort of thinking about, as you're changing in elevation, are you also changing in source intensity or source characteristic? It's very, very challenging to think about, but you raise an important point.
It's also that concentration is quite much higher. It's another question, but how much higher is it in those areas where that boundary between the inversion?
Yeah.
I think anybody's looked at that.
I'll just make a brief comment, but I think that that's one of the active areas of research that we at NIWA are definitely interested in. It's a major issue for New Zealand. In the Christchurch case...
Just say explicitly what that major issue is for the microphone, please.
To reiterate, I think undulating topography, pooling of wood smoke in basins, in valleys, and a variation of exposure with elevation is a very big factor in exposure to wood smoke. Just in the Christchurch study that Jane was talking to, we deliberately didn't survey the whole of Christchurch, but the inner area, which is dead flat. That was semi-deliberate. Any further questions?
We've got an online question, which could you please repeat after me?
Sure.
So how have the political issues got within NYC, and did you have any major controversies, and if so, how did you deal with them?
Okay, thank you. The question that just came in from online is, what were the major political issues that were raised in New York and how did we deal with those? I am actually going to step back from that issue because I no longer work on that study as a representative of New York City Department of Health. So I really, I'm not sure that it would be appropriate that I speak to the politics around that study. What I will say is that it was tremendously influential data that we were able to produce, and very, very high quality models that held up to a lot of critique. And that became very, very important as the policies were developed, and certainly as is policy development around the world certainly went through its challenges. I will say one of the most powerful things that we did do in that study was we released maps that were specific tracers of specific sources of concern in New York rather than PM overall. And that made it much more precise in identifying what sources were really important. So that's one thing that we want to continue to think about in Christchurch and Auckland.
Any further questions? A second question from Mike.
So I guess I presume that there's a high prevalence of wood burning. And do you have any further plans to assess what that means for indoor air environments? Or have you already done that perhaps? Because I think, if you're going to build this into an epidemiological study, that could be a very important source of variation.
Awesome, absolutely. Do you want to talk about Rangiora?
I'll speak to that directly. I think we're very conscious of the fact, particularly in New Zealand, that when people are burning wood, it means they're indoors. But most of the exposure is probably indoors. So we've had a fairly lengthy research program developing low-cost means of monitoring PM in large numbers of homes, which is still ongoing, and it will hopefully be the subject of a future webinar in this series. But I think we found in preparing that research work that there is a widespread expectation that people are protected from wood smoke inside their homes. And what I'll say from now, from the sort of a preliminary pilot study data we've got, is that's generally not true. They are not protected. So more to come on that issue.
Yes, I changed the way that I was burning wood in my own house because I was testing a pollution monitor just by chance. I saw these enormous spikes in carbon monoxide that were happening.
Yeah, and I'll again, just the microphone, I'll just reiterate that comment that when you do, as researchers, we often do measurements in our own homes as part of the life, and it can be quite scary to see what sort of levels of pollution you can monitor within homes. And I'm generally of the belief that the general public will find that interesting, surprising, and could be a strong motivator for changing the way we heat and ventilate our homes. If there's no further questions online, then I think we'll wrap up there, and I'll just again make the final advertisement for the Wood Smoke Researchers Network. We have a website where you'll find this talk and all the other talks in the series, and we're planning more in the future. So thank you very much for viewing online, and thank you very much for those here in Auckland. And thanks again, Jane.